begin our new section in Chapter 7, Section 7-2, and we're going to call this section Relative Atomic Mass. It looks kind of a busy chart, okay? We've got video 16. This is page 234 through 236 in our textbook. Before we start talking about atomic mass and so forth, one of the things that I couldn't remember, I kept getting confused with isotopes and ions, so we got to keep in mind that isotopes are the new atoms with a different number of neutrons in it. That's what makes up the variations in isotopes, and that's why we have to find an average number for a given atom. Atoms usually occur in nature in different forms, and the thing that makes them different is the number of neutrons in each one, okay? Ions, on the other hand, are simply plus or minus electric charge. You change the number of electrons outside of it and it gets charged up. We'll get involved with that later when we do some analysis of these in a spectrometer. And what we want to do is talk about average atomic mass. That equals the average, the weighted average AMUs. The AMUs, you recall, are the weights, number of grams per mole of each atom. And on the periodic table is generally a weighted average of various ions of that atom. Okay. So if we have a problem like this, we're going to study copper, and somebody did a study and found out that copper is made up of two isotopes. Isotope Cu-63, and that's almost 70% of the copper is made up of Cu-63, and 30% of the copper is made up of Cu-65. And you can see Cu-63 and Cu-65. Cu-65 has two more neutrons in it. So when we looked at the AMU of each isotope, copper-63 had an atomic mass unit of 62.94, the lighter of the two, and Cu-65 has two more neutrons and weighs 64.93 atomic mass units. This number, percentage number, let me point out that the percentage of each isotope is called the abundance of each isotope. So in some of the analysis that you'll see online, they refer to abundance. So that's how much of each. And when we get into molecular weight, we're going to do the same thing, find the abundance of each of the elements. So the question is, find the average AMU of copper in grams. And so I have to make up a table and take the information I have for each isotope, and I lay it out like this. Copper-63, that's the isotope, and then the percentage, I have to put that down as a percentage, 69.17%. And I have to convert that to a decimal, and the reason we put it in here is because sometimes there's very little of another isotope, and people are having trouble converting to decimals. Converting from a percentage to decimals, you recall, you just multiply this by 100, or divide it by 100, move the decimal 2 places to the left. Okay, so you can see on the 30, I'm going to move it 2 places to the left. I end up with 0.3083. And when we're analyzing a given element, we want to add up all of the percentages and come out with 100. Otherwise, we'd be missing something, and then our answers wouldn't mean very much, okay? So I take my AMU of each isotope, and I'm going to multiply the AMU times the percentage, or the decimal. That tells me how much of that I have in my final copper, and so I end up with 43.536. That's 69% of 62, 43.536. 30.83% is going to be 20 0.018 AMU. That's how much I'm going to have in my final copper, and I add these together and I end up with my final average of 63.554 AMU, or grams per mole of copper. Now the last thing they ask you to do is to see, is that a reasonable, can I verify that that's the right answer? Well, they want you to just round things off, and what I did is I made a little scale up of the various weights that we can have, and I on my scale, on my mass scale, I got 62, and I start off with copper that weighs 62.4, so I plot that on my scale, and it's just before the 63. I can locate the weight of that. I do the same thing with the heavy isotope, and you can see where that's located. And all I do is take my average, and notice where my average is. Should be someplace in between these two, and it's a little bit closer to the smaller number, and as you can see, well, we have much more of that, and so it should be. So this is enough to verify that we're in the ballpark. If you get a number that's like 0.4 or 800 or something, right away you know you probably made a mistake with the decimal. Okay, go back and take a look at it and correct it. So this should help you do the only two problems to do on page 236, and have fun.